Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a pleasure to welcome Jerry Zhu today. He's an assistant professor at Wisconsin, and he's going to be talking about adding domain knowledge to latent topic models.
Thanks,
Jerry.
Chris. Okay, so let's see. So first, let me thank my collaborators, David and Ojeski, who was my former graduate student who did most of the work and actually made most of the slides here. He's at Livermore Lab now, and then Mark Craven, Ben Leblet, and Ben Recht all helped with the project and funding agencies. Okay, so let's see, how many people are familiar with latent Dirichlet allocation here? Just want to get a sense. Okay, thanks. But let's start from somewhere else. Let's start from Times Square. This is New Year's Eve. What happens there on New Year's Eve? People partying, and this big ball is going to drop. And what you probably do not know is, for the past few years, the organization which runs the party also set up a website to let people type in their New Year's wishes. Okay, so it's a one-line thing, type in your New Year's wish, and they will print it, cut as confetti, and drop it when the ball drops. Okay, that's very nice. And fortunately enough, we get a hold of the data set. So we have people's wishes. Can you take a guess what is the most sort of frequent wish? Right on. Okay, so the most frequent one is peace on earth. Now here is a random sample of wishes. Okay. Let's see. So on the break, getting into university, safe return of my friends. So this particular data set is from 2008. Okay. Find a cure for cancer, to lose weight and get a boyfriend, and so on and so forth. So since we will be talking about latent topic modeling, we're going to treat each wish as if it's a mini document, and we're going to look at the topic that it belongs, right? So you can get a sense, like the first one is about peace. This one is about getting education. That's about war. This one is a little bit interesting because it has a mix of two things, and that's what topic models are good for. It can model documents which contain multiple topics. Okay. Now, as we are all familiar with, if you do a, can we lower the lighting a little bit? Yes. So what you're seeing here is a simple frequency analysis of the whole corpus. Okay, thank you. Oh, that's very. That's fine. Can people see that? I mean, it's okay. It's okay. So, as you can imagine, like the word wish is very frequent. Peace, love, happy, and so on and so forth. Okay. But it has many things mixed in it, right? So the goal of latent topic modeling is to say that, well, let's throw the data at a model, which we will explain later on, and we will get some interesting stuff out of it. I'm going to show you some topics that we recover from using latent Dirichlet allocation. Okay, and by a topic, I mean a multinomial, a unigram distribution over your whole vocabulary. Okay, so what I'm showing here, for each panel, that's a distribution, a unigram of probability of a word given that particular topic. Okay, and the size, of course, corresponds to the probability. You can get some sense that the first one is talking about troops. So troops coming home, God bless our troop, and so on. This one, you see Paul there. I think Ron is there. Ron Paul. For some reason, his name showed up a lot in 2008's New Year's Wish. Okay, this one is about love and so on and so forth. Okay, all right. So latent Dirichlet allocation, or in general latent topic modeling, has many interesting applications, and mostly I would say in the form of exploratory data analysis, just to see what's in the data. The way to think about that is it's very similar to clustering, okay? But instead of cluster a big document as a whole, you're looking inside it and see what composition that document has. Okay, so there has been a lot of different ways that people use that. Okay, before we review that model, let's have a really quick statistical review. So a Dirichlet distribution is a distribution over a d-dimensional simplex, which is a probability distribution. Okay, so you can think of that as a dice factory. You can draw a die from it, okay, and it's going to be a d-dimensional die. In this example, we have a 3-dimensional Dirichlet with parameters 20, 5, 5. The draws from that are going to be a probability distribution over 3 items. Okay. Now, one way to visualize that is to draw the triangle, the simplex here, where A, B, C are the different, the 3 items. And the blue dots are samples from this Dirichlet. Okay, so if a dot is close to A, that means the probability of A is closer to 1, and so on and so forth. Okay, so from a Dirichlet, you sample a die, which is a multinomial. Okay, so in this case, we show this particular multinomial 0.6, 0.15, 0.25, which corresponds to the red dot there. From a multinomial, you can sample a document. Okay, so that's the bag-of-word model. And in this case, let's say the document length is 6. You happen to get this. Okay. One thing that's good about Dirichlet is computationally it's very convenient, since it's conjugate to multinomial is conjugate to Dirichlet. Okay, so people like it. Now, with that, let's quickly review the model. Okay, many of you are familiar with that. I just want to remind you all the symbols. It gets messy a little bit. So this is a generative model of a whole bunch of things given 2 hyperparameters, alpha and beta. So here's how it works. You want to create a corpus. This is what the generative model is about. So what you start with is you start by saying, I want big T number of topics. So right here, imagine you have like 100 topics you want to use. Okay, each topic would be a multinomial distribution. Okay, or think of it as a die over the vocabulary. The way you generate each one of those die is by sampling from a Dirichlet with hyperparameter beta. Now, this beta would have the dimensionality of your vocabulary, which could be, let's say, 1 million. It's a pretty big thing. Okay. So by doing that, now you have a die with 1 million faces, right? Each face has a word on it, okay? So you have one die, and then you sample 99 more dice from it. So that's first how you prepare the topics. Then, with those dice, you're going to generate documents, and it goes as follows. For each document that you're going to generate, first you sample a parameter called theta from a different Dirichlet distribution with a parameter alpha. Okay, and this Dirichlet distribution has dimensionality 100. Okay, it's going to be a mixture of those dice. So for this document, you're trying to decide how often am I going to use each topic. Okay, so that's what that die is for. Once you have that theta die, which is a 100 face die, now you go through each word position in your document. And you do the following. So for the first word position, you're going to sample its topic index, or in other words, which topic die am I going to use for this word position. And this is sampled from that multinomial theta, that 100 face die. Okay? So let's say it's topic 33. Okay? Then you are going to actually generate the word at position 1 by sampling from the word die, multi-face die, the 33rd die of that. So you throw that one, get a word. Okay? Then you repeat in this way to generate the whole document and the whole corpus. Okay? So that's the generative model. And the way we use this generative model, is by condition on let's, for simplicity, assuming you know of n beta, the hyperparameters, but condition on the corpus W, and you want to infer either Z, which is for each word position, which topic did it come from, that hidden quantity, or perhaps more interestingly, you want to infer theta, which are the 100 topic dice, and phi and theta. Okay, I would say phi is the more interesting one. I put a little reminder there on top, so if you want to remember what those symbols are. Okay, so as we go along. All right. Any questions? No. So please feel free to interrupt me at any moment. Okay. All right. So what is this talk about? Now, LDA by itself is an unsupervised learning method. Okay, you give it a corpus W. Okay, you actually have to give it something more. You need to give it alpha and beta and maybe the number of topics, big T. But you don't give it labels. Okay, so it's unsupervised, and it's going to recover those parameters phi, theta for you. Okay, in this sense, it's very similar to clustering. Okay, now because it's unsupervised, sometimes the result can be unsatisfactory. Okay, in particular, a domain expert who is interested in a particular scientific problem, think of like a biologist looking at PubMed abstract, might have some particular idea in terms of like what kind of topics he is looking for. Okay? He has some prior domain knowledge that he wants to constrain the latent topic modeling process. And this is very similar to clustering, where in many cases a domain expert has some knowledge of which items needs to be grouped together, for example. Okay? So there is a need to incorporate domain knowledge into the latent topic modeling process. Now, there has been a lot of variants of LDA which allows people to incorporate different kinds of knowledge. But I would say most of them have a problem in that they need intensive machine learning hacking, okay, to get the model to work. And that means if a biologist is interested in incorporating a particular kind of domain knowledge, he needs to first find a machine learner. Okay? He cannot do that himself. So the talk that I'm going to present is about how to do knowledge plus LDA in a user-friendly way so that anybody, any scientist, not machine learning researchers, can incorporate their knowledge. Okay, and we're going to talk about 3 models. Number 1, topic Inset. Number 2, Dirichlet Forest. Number 3, Fold.all. Okay, so first one. Okay, I'm going to start with a slightly unconventional example. This one not about documents, but about software debugging. Okay, and some of the work is done at Berkeley and here, Alex Zhang, Microsoft. Okay, so here's the idea. You have a software like, I don't know, IE. Okay, you want to see there are bugs. You want to see where they are and so on and so forth. One way to do it is to insert a lot of probes into the code. So you instrument the code. And the way you can think of that, so the yellow things are probes. They're specialized counters. So you can imagine like at different locations, you insert different counters. And whenever the program gets there, the counter gets added by 1 and so on and so forth. And at the end of the program, no matter whether the program crashed or not, you are able to recover those counts. Okay? And let's also assume that you just want the counts, the aggregate of how many times this line is executed. You're not interested in, or you cannot keep the actual executing sequence of things. So it's very much a bag of word notion, right? So this is the setup where the predicates acts as words. You have a bag of predicates. And a software run would be a document. Okay. Now, for this problem, we actually have some extra knowledge, which is whether each run crashed or not. So you have a label. Okay. So you have a label, you have a bag of word of something. a straightforward idea would be, if you want to do latent Dirichlet allocation on this, is to collect all the failed runs, all the crashed runs, look at their backward representation, run the LDA on it, and say, okay, could you please recover 100 topics? I'm going to look at those topics. The hope is maybe some of those topics would be indicative of bug behavior, like particular lines where it's abnormal in some way. Okay? So yeah, that's a very reasonable goal. But what happens in reality if you try that is you don't get nice bug topics. Instead, you would get topics that are, in some sense, much stronger. Those are normal usage topics, like different function. Maybe you open up a web page, maybe you print a page, and so on, corresponding to those kind of things. And those are much more frequent, and therefore they dominate the topics you're going to get. Okay? To illustrate that, I'm going to show you a synthetic example. So the way to see this is I'm creating a figure which is a 5 by 5 square, and each pixel corresponds to a predicate. Okay, so we have 25 different predicates. And I'm actually going to generate software runs. So the way I generated it is by using a bunch of topics, which are multinomial distributions that will generate pixels here, 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 but not there. Okay, so that's that topic. I have, 8 topics there, and 3 buggy topics here. Okay, so I can sample documents, both successful documents, runs, and crashed documents from that. And this is what you would see. Okay? So remember, a document is a mix of all topics. It's very hard for us to see what's actually going on here. And you don't see those things. Yes?
In this case, are you doing the LDA completely independently, like you're not paying attention at all to the other set when you're doing...
So far, I'm generating it. So I'm using LDA model to generate documents.
But you're doing the decomposition independently for label 1 versus label 0. Like you've just taken the group label 1, not paying any attention to the...
Yes. So yes, and in fact, I think this will answer your question, right?
Okay.
Now I'm going to run LDA on the crashed runs. It's more than this, but I'm going to run it on that. And here is the topics that I recover. Notice I actually used the correct number of topics. But I made the data set so that these topics are going to be more frequent, and therefore they somehow mask the bug topics. You don't get those nice things. Okay? All right. So what should we do? So here's a fairly simple idea. Since we know which runs crashed and which did not, we can actually jointly model both kind of documents. And here's intuitively what I want to do. Let's say I want to use big T topics overall, but I can sort of set aside a smaller number of topics, small t, and say that those are usage topics, and the remaining ones are bug topics. Very importantly, if a run succeeds, I'm going to say that for all positioning in successful runs, it can only use usage topics, and it cannot access those bug topics. Okay? While for crashed runs, I will allow them to use any topics that they want. So this is an additional constraint on top of standard LDA. Okay? The hope is, by requiring this is the case, you force the first small t topics to model general software behavior. And then the remaining ones, hopefully, will capture the remaining bug behavior. Yes?
But is there any constraint or cost in terms of the difference in distributions between the different sets there? So
no, we didn't do anything at all. It's as simple as this.
So they could overlap, and that would
They could overlap,
cost.
definitely. We didn't do anything sophisticated. It's just like say, let's constrain that in this way. Okay. Now, this is the new result. Okay. Turns out if you do this and say, okay, let's have the first 8 be the usage ones, and only these can get the buggy runs, you actually get something quite sensible. Okay? So this is a very simple example to get started with. And here are some actual run results. It's going to, yes. Yes.
One more. This is a question, but why not have the two sets of topics destroyed? Why not say 1 to t and t plus 1 to big T?
Right, because both runs would contain normal usage. Like for both runs, somebody would open a browser, right, or do things like that. So you have the common element. You just want to group the common element in the first small t, and then let remaining ones explain bugs. Yeah. Yes?
On documents,
yes.
Would this be the same as modeling the background distribution?
Yes, it certainly sounds a lot like that. In fact, I imagine one can explain that it that way. So the first small t is the background model, and the remaining one is special. Okay, I'm going to skip this. This is real software. Like people actually, their job is to insert bugs into programs and run this, and we were able to distinguish that. Okay, you can easily extend this idea to the more general topic inset constraint, where you say that here's our additional knowledge for each word position in the corpus. We can set up this set CI, which can be arbitrary. It's a subset of all topics, and you constrain it such that the topic index for that position must be in that set. Okay, so this can actually encode quite a few different domain knowledge. For example, CI could be a singleton. That would be like saying this word must be in topic 3. Okay, and this is very easy to do. So one inference method for LDA is so-called collapsed Gibbs sampling, where you are given W of beta. You have to infer Z, and you also need to integrate out phi and theta. That's why it's called collapsed. And you do this in a Gibbs sampler fashion. You sort of go through Z, go through all word position, and change Z in that order. Now, the black part is standard LDA collapsed Gibbs sampling, but the topic inset knowledge you can easily encode by inserting an indicator function there. Okay, so it's an indicator if the value of this ZI, the ith word, is in the specified set. You let this term be 1, otherwise it's 0, so you essentially forbid that Gibbs sampling to take values outside the set. Okay, so you can do that fairly efficiently. And you can also relax this hard constraint to something that's slightly softer, so that it's not strictly in the set, but you pay a penalty there. Okay. So this is a warm-up of how you could start to add interesting knowledge to topic models. Now let's move on to the second model. Okay, it's called Dirichlet Forest. I'm going to actually present the result first because I think it's kind of interesting. This is how people can use a model like this to do interactive topic modeling. Okay, so recall that we have this New Year's wish corpus. If you run a standard LDA on that corpus with 15 topics, t equals 15, you get something like this. And what we're showing here is each row is the most frequent word in that topic. Okay, so let's take a look at those. One thing you might immediately notice if you work in natural language is that we get a whole bunch of stop words mixed in there. Okay? And this is usually undesirable because the topics are not as pure as or as informative as they could be. Okay? Now, there has been a lot of ways to handle stop words. The simplest one might just be you pre-process your corpus so that you remove all stop words. But here we're going to do something else. Imagine a user looking at this result and say that, hey, we have too many stop words in here. Let's get a standard stop word list and say that please exclude all those stop words from normal topics. Let's sort of merge them into a single topic, isolate them. Okay? So this is an operation that a user can do. The user is going to do an isolation of, in this case, we actually use the 50-word stop word list. Okay? And we let the system rerun, okay, but allow it one more topic. So now we have 15 topics in all. Okay? What I'm showing you here is the result of this rerun after we somehow do the isolate operation. And these new topics, 2 topics, are now responsible for stop words. Okay? So 2008 is a stop word because that's the year of the wish corpus. Yes?
Why are there 2 topics?
Yes, that's because all we did is, you will see how we do the isolate operation. And we didn't really say that please move everything into this one topic, but we simply say please make sure those stop words are not in the same topic as other words. Okay? It turns out LDA wants to use 2 topics to explain those stop words. Now, if you look at the result, it's much better now. But you might notice this particular topic, which I said mixed, go, school, cancel, cancer into well-free, cure, college. What happens is it's a mixed topic of 2 things. One is you want to get into college. Second, you are wishing somebody to be cancer-free. So these are 2 different things. So we will be able to say that let's split here 8 words into 2 groups. So these are, imagine those are like seed words for those 2 topics. You're going to say that let's split those particular 8 words, but hopefully they will create new topics and drag other relevant words into their respective topics. And this is what happened. So they are marked here. We allowed one more topic to accommodate for that. And you see the green words are the ones we used in split, but yet also moved other relevant words in there. The reason you see mom, husband, son here is because most people are wishing, like, we hope mom to be cancer-free. So that's considered the same topic. Okay. So again, now you see the first one and the 10th one is kind of all about love. And you might want to say, let's merge these 2. Okay, so we can, again, do a merge operation by specifying a few keywords. And if you do that and rerun the whole thing, now we have a single topic there, which is much more pure, except lose weight. Somehow that's tied to love. And you get the idea. Okay? So you can use this in a way that's interactive to shape the topics that you want. Okay? Yes?
When you do a merge operation, are you saying that 2 topics get merged or 2 sets of words?
2 sets of words.
So how's that different from isolate?
So you're asking for 2 sets of words which were originally in. I mean, it's not quite different. I will show you how it's encoded differently. It certainly has the same flavor, but it's encoded slightly differently. Okay, and you can do this by changing the model, the standard LDA model slightly. So recall this is where we sample the document dies, okay, the 1 billion sided die. Instead of using a Dirichlet dice factory, I'm going to use something called a Dirichlet Forest distribution, which will give you something that cannot be achieved by Dirichlet. Okay, so what is this good at? It's particularly good at encoding pairwise relations in the form of, for example, must link. This is term borrowed from clustering, but what here it means is you want 2 word types U and V to be in the same topic. Okay? But what does in the same topic mean? Because a topic is a multinomial distribution over the whole vocabulary. Any two words are always going to be in there with non-zero probability, right? So by must in the same topic, we mean the following. We don't like the case where one word has high probability, the other has low probability in a particular topic. They could either have both high probability or both low probability. That's it. Okay, so that's what we want to enforce in terms of must link. And similarly, you can enforce cannot link. You do not want these two words to be presented in the same topic, but again, they will. So what we're really saying is you want one to be large, the other to be small. Or both small, I think. But you cannot have them both high. Yes?
So maybe I'm jumping ahead here, but it seems like these kind of things are very difficult to put at the feature level, but easier to put at the example level. Right? There are often cases of usages of words that you forget. I imagine in any domain where the features, sort of making these statements on features seems very hard and almost to preclude what you want to actually do with the data analysis.
Yeah, so I agree with you to some extent, especially when you exhaust the first few easy features, then things get harder. And our model here does not address that. So here everything is strictly on the features. Okay. All right. Now with these two, you can create the higher level operations. For example, split. You can say that I have a group of words, I can split them. The way I do that is by creating must links within groups and the cannot links across them. Merge, very simple, just put must links among the words. And isolate, you put cannot links from the words you want to isolate to all high frequent words in the current topics.
Sorry. So for split then, you need to then encode for each, basically for every pairwise set over.
Okay.
Okay. All right, so here's why you cannot do this with Dirichlet. Okay? Let's imagine you have a vocabulary school, college, lottery, just a three-word vocabulary for simplicity. What would a must link school, college look like? That means you want to generate a multinomial such that school and college either both have 0.5 probability or 0.2 or 0.1 or 0. Like they're somehow tied in this fashion. Okay? And if you look at the simplex, this is what the density look like. You want this. Okay? This, however, cannot be achieved by Dirichlet. Okay? If you try to encode it with Dirichlet, you will get things somewhat like this. Okay? And the reason why you cannot do that is because in the Dirichlet distribution, the variance of each dimension is tied to its mean. Okay? So you do not have the extra degree of freedom to encode its variance. Okay? And the way to get around it is to go to what's called a Dirichlet tree distribution. And, well, Tom Minka here did something on this too. In the Dirichlet tree distribution, you have your vocabulary here, but you put a tree on top of it. Okay? It's a tree where you have positive edge weights. And the way it works is the following. So let's see. The weights can be arbitrary, but in this example, I made them special. So you have eta. Whenever you see eta, that's a big number, so 50. So you have 50 here. And then this one is 2, that one is 1. Okay, so let's imagine we have a tree like that. The way you generate a multinomial distribution from a Dirichlet tree like this is the following. You start from the root, and you don't look at the subtrees. You just look at its children's weight and treat that as a Dirichlet distribution. Okay? So you're going to draw a multinomial of 2 elements from this Dirichlet. Okay? So let's say we do that, and we happen to get this. Okay, that's the multinomial distribution we get. Then you go down to this internal node, and at this place, you're going to use these as the Dirichlet parameter, and you draw another multinomial. Okay, so let's say that's that. And the intuition is this is the probability mass that you get here, and you're going to split it according to that. So you basically multiply the numbers along each path. That gives you the final probability. Okay? And because of this construct, what we will see is the following. Here, you pretty much get a fairly uniform distribution in terms of the weight distribution. But once you go down here, because these are large and the property of Dirichlet is you will evenly split them, right? So you get the desired behavior. This is just to show you things are a little bit messy, but it's actually quite nice. You still get what you want in closed form. And in particular, this important quantity delta for each node S, which is the in degree of a node in the tree versus the out degree, minus the out degree of that node. If that difference is all 0 for every node in the tree, you actually recover a standard Dirichlet distribution. Okay. When it's not 0, you get more interesting behavior. Furthermore, this Dirichlet distribution is nice. It's conjugate, again, to multinomial. So it's convenient to work with as long as you're careful about bookkeeping. Okay? So this is how we're going to encode a must link. Basically, whenever you have a must link, you're going to say these two words are must linked. You're going to create a subtree with very strong but equal weights there. And then on top of that, you're going to create a weak edge, but with the number of number of children number of leaf here, and the number of leaf here. So that evenly splits that probability mass. Okay, this will give you samples like that. So that's must link. Now recall cannot link, where you do not want two words to both have high probability. That one is again impossible to compute to encode with Dirichlet.
So one question: so the eta and the beta in the tree that you had before, did you just determine those empirically and then just use some fixed?
These are yes. So that's what we did, and you can think of them as knobs that the user can tune. So yeah, we didn't learn them. We set them. Yeah. 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 All right. So cannot link, for example, cannot school and cancer. What you really want is this kind of behavior for 3 vocabulary word. You want either the probability, multinomial probability to concentrate on school, or it can somehow arbitrarily split the mass between these 2 words, but not on school. Okay. So any dot there is okay. As I said, this cannot be easily represented by a Dirichlet, and it cannot even be represented by a Dirichlet tree. A single tree is not sufficient. What you will need is a mixture of trees, therefore the name Dirichlet Forest. Okay, I'm going to show you with one example how things might look like. It's a little bit involved, but here we go. Yes?
Can a Dirichlet Forest model anything? If you plot some other... It's completely general.
It's it's a mixture of Dirichlet tree, that's it.
But then you can get any density you like. Is that true or not?
Let's see.
So there's like 3 blobs on the left and a nice line on the right.
I think it should be. Yeah, I think it should be. Yeah. All right, so we have a vocabulary of A to G. And here are the links that we want to satisfy. A must link between A and B, and a bunch of cannot links. Okay. Now the thing is, okay. So here's how we do it. Write down all the nodes. And A, B, those are must linked. I'm going to treat it as a single node there. It's like glued together by must link. I'm going to have all the red edges with a cross representing cannot links. So that comes from my knowledge. This is the graph we start with. So we have multiple steps. Step 1, let's identify connected components. Okay? The reason we want to do that is because each connected component, like this box, can be modeled independently of other connected components. So we will then focus on one of these guys. Okay? Then inside each box, we're going to flip the edges. So instead of cannot link, you turn on the opposite, the complement edges. Those are the can links. That means these words can appear with high probability together. Okay? You identify the maximum clicks of those within each component. So ABC is a big click, and D is another click there. The interpretation, again, is each maximum click, like ABC, those represent the maximum collection of words that can co-occur with high probability. You cannot add any other things from the same connecting component, otherwise you are going to violate one of the cannot links. Okay? So that's that. Now with that, we are going to create or sample a Dirichlet tree. And the way we sample this tree is by constructing its subtrees in the following manner. We're going to intuitively say that for this box, I'm going to either select this click or that click, okay? Allowing the selected one to share high probability and denying probability match to anything else. Okay? So the way I'm going to do that is to choose between, for this particular one, I have two maximum clicks. I'm going to have two candidate subtrees. And there, the trees, if you don't see a number between the edge, imagine it's edge weight 1 and eta is something big. Okay? The reason we have this design is because recall when we sample that Dirichlet tree, when we're here, if you see eta, which is big, and 1 there, you're going to very likely apply all the probability mass down to the eta branch. Okay? And with very few probability mass, very little mass to the other guy, D. Okay? So this, if you choose the left subtree, you're saying essentially that you want all probability mass to go to ABC, but not to D. And the second one, vice versa. But you have to make the choice at this moment. So you sample the tree like that. Let's say we flip a coin, we choose the first tree. Once we're there, we need to further distribute the probability among A, B, and C. And here, we're just going to give it any chance. So uniform, not uniform, but a Dirichlet with all ones. So it can generate a uniform distribution over the simplex space. And finally, so at this moment, we're safe in that we will satisfy all cannot links within the first box because you didn't give D any probability. And finally, we're going to, because there's a must link between A and B, we're going to again do this trick and let them evenly split the probability mass that reach that AB node. Okay, so this is how you do that branch. You can do the same thing for this, the second one. Here, the choice is over either giving all probability mass to E or to F. Okay, and so on. So if, let's say we select the second one, the effect is you will give probability mass to F and not to E for this tree. Okay, so you do this, and then you will have sampled a Dirichlet tree. Okay, and then you use this Dirichlet tree to generate a multinomial. Okay, that will satisfy your must link and cannot link. Many of you will have noticed that the procedure is combinatorial. Okay? So in theory, things can get really bad and you get tons of candidate trees, exponential number of them. But in practice, we see very small numbers. So it's just like there's a gap between theory and practice.
In practice, meaning what kind of data?
Smallish data. And like the data I showed before, the wish and the split and the merge and so on. So all those operations.
But are you individually then going through the combinatorics until KL divergence is close enough, or?
No. So you do this, right? You do a Gibbs sampling, but now you sample both over the Z assignment, topic assignment, as well as the tree index. So you're sort of massaging the trees for each topic. You're selecting which subtree you use along the way, and you can adjust that So that becomes part of the variables you do in Gibbs sampling.
I see. So the actual forest that you have is changing.
Yes, exactly, and that's part of the sampling. Okay, and just to show you that this is how we sample the forest. Again, a lot of bookkeeping, but not terrible. Okay. All right, so in the last 10 minutes, let me quickly go through a third model, which I promise you is not as hairy as this one. Okay. All right. The motivation is, well, these are okay, the methods I've talked about. They can encode certain knowledge, but they're not general enough. Okay, I want to have a really general way to specify domain knowledge. Or not me, but domain experts. And the solution is, let's go to first-order logic. A domain expert can usually specify his knowledge in first-order logic form. So the advantage is it's easy for an expert to just write down a knowledge base in logic and say, okay, here are the things I want to satisfy in terms of the topic. Okay? It's very general. In fact, it can encode several existing variants that's being proposed in the literature. Critically, we want efficient inference. That's the difficult part. Whenever you involve logic, inference could get very hard, but we will see an efficient way to do that. So for those of you who are familiar with Markov logic network, the relation between our Fold.all model and that is the following. You can view Fold.all as what's called a hybrid Markov logic network, which is a Markov logic network, which is a Markov random field constructed from logic, multiplied by a likelihood term which involves continuous random variables. Okay? And those would be our psi and theta. Okay? So it's an instance of that, but we have our specialized optimization scheme so that it's efficient. Okay, so here's how you think of the problem. Here's how you encode domain knowledge in logic. So let's think in terms of logic. You have predicates, which are Boolean functions. For example, you can design Boolean functions big Z. It takes in two arguments, I and T, where I is a word position and T is a topic index. Right? So you can say something like Z, I, T is true if word position I takes the value T, or in English, the ith word comes from topic T. So that's the key predicate, and we do not know that. We will need to infer that. Besides that, you can define, and this is the power of this approach, you can define arbitrary observed predicates. Some of the predicates are like things like before, where you have WIV, the ith word takes value V. Okay, it's like just the ith word is this V word. But then you can put things like document boundary in there, that's D. The ith document, the ith word position comes from document J, okay? Or has label JL, so document J has label L, or even sentence level label, you say the ith word comes from the K sentence, and so on and so forth. So you can put in any observed things that you have in this form, okay? And we will use them. Now the key is you're going to use this to write rules in logic, call those size. You can write big L number of rules. Each one is associated with a positive weight lambda. Okay, that's the standard Markov logic network setting. For example, I have two rules here. The first one is weak. It has a weight of 1. And this rule says for all position I, okay, if this is true, that means if the ith word is embryo, implies its topic is 3. So basically this says whenever you see the word embryo, put it in topic 3. But it's a somewhat weak rule and it can be overridden. So these are, think of those not as hard constraints, but as preferences. Okay. The second one 100, so that's a very strong rule. You cannot violate it. And it has a whole bunch of universal quantifications. For all position I, position j, for all topic T, if the ith word is movie and the jth word is film, let's do not put these two words in the same topic. So they cannot be in the same topic T. This is exactly the cannot link, but expressed in logic form. So we put a cannot link between the words movie and film. These two words need to have different topic. They need to go to different topics. Okay? Yes?
This is the positive weights that you have there for L2 being 100. Sorry, is that given by the domain expert or
Yes.
that's learned?
Yes. It's right now it's given by the domain expert. Okay? We didn't look into the learning issue with that.
So what range of numbers do you allow, and do they end up being kind of on the extremes? Do you see any?
Right. So this is a fairly empirical question, and the answer is we tried a whole bunch of numbers, and you clearly see that once you tune up the numbers, that rule gets enforced. But setting them appropriately is an art. Okay.
Right. So that's the thing. I mean, I work myself with rules that have weights associated with them, and I had weights 1 to 10.
Mm-hmm.
Kind of the majority of the rules had either 9 or 1,
Mm-hmm.
and then there was some squishiness in the middle, where I could say, okay, 3 or 7. But
Right.
you don't get an even distribution over all of these.
Yeah,
weights.
here we don't even estimate the weights, so we don't have a distribution. It's all user provided. And what we can do is we can assign a meaning to the lambdas if we normalize the terms appropriately so that they are more interpretable. Okay, you will see how they come into play really soon. Okay, so if you're familiar with logic, you know that this is first order logic. You have universal quantifiers for all. And the way people, like one simple way of doing inference here is to do something called propositionalization, which turns first order logic into Boolean logic. And that simply means for all combinations of free variables in your rule, you just assign it a particular number. So you do this exponential explosion and generate what's called a grounding G, small g, from a particular rule. So this big G is the set of groundings, and small g is a particular grounding. So for example, this would be a particular grounding where we look at word position 1 to 3 for movie, word position 4, 5, 6 for film, and the topic in question is 9, and so on. So you actually have to do, in this example, you have to do n squared times big T, that number of groundings, which is a huge number. Okay? But in theory, you can do that. So you turn everything into Boolean logic. Okay? So this set, big G, just keep in mind that could be a huge set. Once you do that, yeah, that's combinatorial. Let's define this indicator function 1 with subscript that particular grounding, and it takes in the hidden topic assignment that you currently have. Let's say you have a candidate assignment. Well, then you have the natural 1-0 definition. So here's how it is used. This is standard LDA, except that I draw it as an undirected graphical model, a factor graph. Okay? And these are the terms that you will recognize. That's the topic term, document term, and so on. All we do here is to add in this term which corresponds exactly as Markov logic network. Okay? And that corresponds to this factor node, which is a mega node. It takes in arbitrary observed variables. Okay? And it has this form. So you are taking, you have the exponential here. You're summing over all the rules you have. For each rule, you're going to sum over its exponential number of groundings. And then the weight is here. And then that's the Boolean function here. And it's applied to the z in question. Okay? So this objective function is really nothing but a straightforward combination of LDA and Markov logic network. How much time can I go over just a little bit? Okay, I'm going to be done very soon. Okay, so we are interested in, again, inference. So this is the task where you're given the corpus and you want to, and the rules, and you want to infer z. Okay. Now what you can do is you can take the logarithm of the previous probability. That's what you get here. Okay. The black terms comes from LDA. The red terms come from logic. Again, you have the summation. This is the part that will kill us. But that's the objective function. And then you can do, keep in mind that this objective function is non-convex. Okay? And you can optimize it in a simple way. You do the alternating optimization where you fix z first and then maximize this. If you fix this term disappears, and you're doing standard LDA stuff, which is very simple. Okay? You immediately get this. But the other part is you have to iterate and fix those phi and theta, and now you optimize z. Keep in mind, z is discrete random variable, so you get yourself an integer program here, and it's huge, right? So this is the part where people typically get stuck. Like this is where it takes a lot of time to do inference. Okay, but we're going to do this procedure. We're going to iterate, and I'm going to explain how we do this part in a somewhat efficient fashion. Okay. So here's how we optimize z. So we're talking about this step now. Number one, we're going to relax those indicator functions into a smooth function. It's continuous, so we can take derivatives. Okay. The way we do that is the following. So let's take a look at that particular grounding G, which says zi1. The first word, the ith word is topic 1 or not zj2. Okay. And let's say we only have 3 topics. Big T is 3. Okay. So here's how you do the relaxation. Turn that one indicator function into a continuous function. First, you take the complement, logic complement, so you get not this and z. Okay, that's fine. Then you remove any negations. Okay, so for this term, not zi1. Now recall that zi1 means the ith word takes topic 1. Not of that, since we only have 3 different topics, it must be like it takes topic 2 or topic 3. So that's how you get rid of the negation. Okay. Then we're going to turn OR into plus and into multiplication. Okay. But these variables are 0, 1 integer variables. So far, things are equivalent. Then you do 1 minus this. This is the negation. Negate it back. Still 0, 1 variable, but then you trivially allow it to be in the interval 0, 1. So now you have a continuous function. Okay? This is still non-convex, though. Okay? And yeah, if you're curious, the big 1 function becomes something that looks like this. Okay? It involves a whole bunch of variables that's between 0 and 1. Okay? So remember, we're trying to optimize the big Q function. Now we're optimizing over z. So let's take terms that's relevant to z and ignore all constant terms. You get something like this. So this comes from the logic. This part comes from LDA, the part that involves z. Okay. You were doing a optimization problem. This one is a nice one because z now is between 0 and 1 for each element. And all you have to do is to constrain it to be non-negative and sum to 1. So that's nice. But we still have that exponential number of groundings here. So this term is huge. And you don't want to take the normal like gradient step and do that. It's just way too expensive. So the trick here is to say, let's do stochastic optimization and treat this objective function as the objective we're trying to optimize, but the actual thing you do is you randomly pick one term out of these. Okay, so call that term f. It could come from here, or it could come from here. It's going to be a term that involves some z, but it's a very small number of those. So you just take one term out randomly, treat that as if it's the random objective, because if you take the expectation, it gives you back that. So you're going to take one random term out, do a small gradient step, and then take another term out and do it, and so you repeat. Okay, so you do the stochastic optimization in this fashion, take a term out, and you do this kind of exponentiated gradient, which maintains this constraint. Okay, so you just do that, and it turns out that it works quite well for our problems. Okay, we were able to run fairly large logic knowledge base in a reasonable amount of time. Okay, I mean, by the way, you can stop this anytime you want. So as long as you have time, you can keep working on it. Recall that this is the particular rule we said. It's a cannot link. This is Pan and Lee's movie review sentiment analysis corpus. So it's a bunch of movie reviews submitted by people, and we run LDA on that. Okay, but we add this one rule which says let's put a cannot link between the word movie and the word film. And my student David did that because he suspected that people are using these two words differently. Okay? And yes, as you can see, these are the two resulting. There are more topics, but we're taking out the two topics where film and movie are the most frequent. What do you notice?
Negative root as opposed to film.
Yeah, for some reason, film is a more elegant word, right? People associate good words, great, with film, but here you have bad movie, and yeah. So it's kind of strange that you see this. Yes?
I have a question about the semantics of this. Is you have a, because this example is kind of telling, is that, because what you ended up encoding here, even though you're using the fuller logical form, is that it is just a cannot link constraint that you had earlier. And I wonder if you told the domain experts that, hey, sorry, you don't get full logic, you just get must link and cannot link. How much does that really restrict them in terms of the things?
Yeah, that's a great question. Or I think an equivalent way to understand this is to say that what is the power of just must link and cannot link, right? You can create some higher level things like split, merge, and so on. Sure. So maybe it's rich enough for normal usage.
It's pretty rich.
Right? So it's pretty rich.
Yeah.
But on the other hand, the logic has the nice thing that you can claim that pretty much you can encode anything as long as you can write it in a logic form. So you have that sort of peace of mind there. Like, if you want, you can always write complicated rules.
It's true, but I wonder if for real domain experts, if a bit of biologists come in.
That sounds like a great project to work on.
So I think the one example you gave kind of is the thing that immediately comes to mind, which are contextual constraints, right? In this context, these things must, that seems like the thing that I, like for language, would most want to apply, right? To disambiguate your context. And I think Jerry gave a nice example earlier with one of his logic examples. That seems like, maybe I don't want first order logic, but plus kind of like plus context.
Yeah, that's good.
All right. So to evaluate, we want to evaluate two things. One is whether the logic that we specified as extra knowledge, can they generalize to unseen test data? Like the topic you get, can they generalize? Second, we want to see how good the inference is, like how scalable it is. So here's what we did. We have a bunch of data set. I don't have time to go through the details, but they're in the paper. We're going to do cross-validation, but whenever we do training, we're going to do first do Fold.all plus all the logic rules that a domain expert gives us. From that, we will be able to get the topics, right, the phi's. Then on the test fold, what I'm going to do is I'm going to use those topics to directly estimate the the word topic index. So importantly, without using any logic. I'm just going to use the files there to get these. But then once we get the test set these, I can go back and essentially see how much of it fits the logic that the expert gave us in the beginning. Okay? But we did something slightly different. We looked at the test objective queue, which balances both the desire to satisfy logic as well as the desire to satisfy LDA model. Okay? So in general, in this table, that's the test set queue. You want this number to be big. The bigger, the better. Okay? And as you can see, this is pretty good on test set. If you simply run LDA without logic, you get pretty poor result except for this one. Alchemy is where you only enforce logic, but without the LDA part, of course. And so it's not as good, but again, another thing to notice is these dashes are where things do not complete within a reasonable amount of time. So this shows that our method with stochastic gradient is fast enough to work on reasonably large, especially this one, logic knowledge base. Okay.
Yes? So in the logic part, you actually have two steps that basically do the approximations. I mean, the first one is realization.
Yes.
The second one is actually stochastic.
Yes.
So I'm just wondering whether, inject and exact inference will actually give you a greater performance in a sense. I mean, probably not on the large data set, but
yeah.
One of the data set you put in the next slide, which probably,
So let's say we have a column here which says, let's do exact inference. If we can do that on, let's say, smaller large base, how well we would do. Indeed, for the ones that we can complete, the number tends to be slightly bigger than this one, but not too much bigger, slightly bigger. Okay, and it's in the paper. I didn't present it here. But the problem with that is you will have a lot of dashes here because you cannot do that. All right, so here's the summary. I think it's very interesting to inject domain knowledge into an unsupervised learning method like LDA because I think the domain experts really want that. We presented 3 models. They have increasingly more general power. And the key here is 2 keys. One is you really want this to be easy to use for domain experts to create their knowledge, to inject their knowledge into the model. Second, you really want to make sure it runs fast so it's scalable. Okay, that's it. Thank you.